Okay, so we're going to pick it up now where we left off yesterday in chapter 3. This topic is maxima and minima. And so what we're looking for is a maximum or minimum point in a function, if it exists. And a couple of things. First, we had a bit of a Latin lesson yesterday. We saw that maximum, when pluralized, becomes maxima. Minimum, when pluralized, becomes minima. And also the word extremum refers to either a maximum or a minimum. Okay, so in other words, a maximum and a minimum are both examples of what we would call an extremum. So a function can have two types of maximum and two types of minimum. These two, you can see here, these are all what we call local maxima or minima. And sometimes local is also referred to as relative. And that simply means that, for example, here, if you look at x1, this is the point where the function reaches the highest value within this immediate area or neighborhood, as it's sometimes called, or you could even think of it as an interval. You can see clearly that the function does later on reach a higher level, but that's quite a ways further to the right on the real number line. Right here in this immediate vicinity, this point x1 represents our local maximum, and then x2 similarly represents a local minimum, and then x3 is another local maximum. And in fact, we can have any number of maxima or minima, and in fact, we may not have either. The word global refers to the case where that point is not just a local, but the actual largest value that the function will ever achieve. Over here on the right, you can see it's called a global or absolute maximum. And down here in the bottom left-hand corner, this is as small as the function will ever get. And so that becomes a global or absolute minimum. Okay, so this graph, actually right here, this chart is actually pretty helpful. You can see what it means to be a local maximum and a local minimum in the first graph in the upper left-hand corner. And of course, again, it's clear here that while this is the highest point that function reaches in this immediate area, the function does later on reach higher levels. Same thing here with the local minimum. Okay, so that's why it's a local minimum. The other two, we found that this is the highest point that the function will ever reach. That becomes a global max or maximum. And then when down here, this is the smallest, so that it becomes the global or absolute minimum. So what we're going to be doing, oh, and here's a case where there are no extrema, right? It just rises from positive to or negative to positive infinity. And so there are no extrema here. Okay, so the local maximum means that there's some interval over which f of c is the highest value of the function within that interval. Now, by the way, this does not include a and b. It's only the interior points, as they're called. So here you can see in this diagram in the bottom right-hand corner, for the point c, f of c is the highest value that the function will achieve in that interval from a to b. And of course, and I reviewed here the idea of what is an open interval. Open interval simply means that the two endpoints are not included. A closed interval means they're both included. And of course, these last two cases, this third one down here is where we have an open parenthesis on the left and a square bracket on the right. That one means that the B is included but not the A. And then the last one at the bottom means that A is included but not B. And these are sometimes called semi-open, semi-closed. You get the idea. Okay. So anyway, all of the intervals in this section are open intervals, meaning that we do not include A or B. The local minimum, it's again, you see here, there's point C and f of C is 0 actually in this case. That's as small as the function gets in this interval from A to B, and therefore this qualifies as a local minimum. Now, a critical point is an interesting concept. This is the point, a point, potentially where the function reaches a maximum or a minimum. But a critical point can actually refer to something a little different. A critical point can also occur if the derivative is undefined at that point. Okay, so in the bottom left-hand corner here, you see that C is not, or I mean, it is a critical point because the function is undefined due to this discontinuity in the graph. And in the bottom right-hand corner, we have this sharp point in the graph, which means the derivative is undefined. And therefore, this C down here is also a critical point. So a critical point points us to points that, or shows us where we might have a local maximum or local minimum, or possibly a global minimum or a global maximum. It also, though, might point us to where there's an undefined derivative. So what this leads us to is the idea that if f of c is a local extremum, then c must be a critical point. But if c is a critical point, that doesn't guarantee that f of c is a maximum or a minimum. Okay, so here's Fermat's theorem. I think we mentioned this yesterday, this interesting side note about Fermat. His final theorem, as it was called, is the one that was never written down. His proof was never written down, or at least nobody could find it. And it took hundreds of years before anybody was able to prove the theorem that he was referring to. So, but Fermat was a genius, of course. And so, everything he wrote was very important mathematically. But he did have a tendency to scribble little notes in his books. And of course, that's a great way to lose it, whatever you've done. And that's exactly what happened. But of course, he was alive in the 17th century. So of course, there were no computers in those days. Anyway, so according to Fermat's theorem, if f of x has a local extremum at x equals c, and if the derivative exists, then the derivative is equal to 0. Okay, what does that mean? Well, if you look at all these cases where we had a maximum, whether it was or an extremum, I should say, whether it was a minimum or a maximum, in all these cases, and here it's very obvious, if you drew a tangent line to the function at that point, it would be horizontal, meaning the slope is 0. Okay. Now here, though, we had a case where that wasn't true. This C is a critical point, but it is not an extremum because the derivative is not defined. So Fermat's theorem is saying is that if it is defined, meaning that the function is differentiable at that point, then the only way that can be true is if the slope is 0. All right, so here again, we have some examples of this. And then now here's some examples. Here's the pointy one. Let me get this out here so you can see it better. The first one in the upper left-hand corner is a critical point because you can see this is clearly a local maximum and the tangent line is horizontal. The derivative is 0, therefore. The second case, the pointy one, f prime of c is undefined. Now, I mentioned this once before. When a function has a sharp break like that, the derivative is undefined because it means that there's a sharp change from one side of that point to the other. It goes directly from some very steep positive slope to some very steep negative slope. And that doesn't, this is not what the derivative is all about. The derivative represents a subtle or small change on either side of that point. So here, that does not have a derivative. And yet at the same time, though, C is a critical point for that reason. It's just that it's not a maximum or a minimum. And the one on the right here, this one is also true. You might recall, let me just toss this in here. Our old friend, the absolute value of x, we have the same situation going on here. So if C is 0 here, this C is a critical point, but this is not a minimum or a maximum for the simple reason that the derivative here is undefined. Again, that's due to the fact that it's a sharp break between the slopes of the two sides on either side of that point. Or the other way to think about it is that the limit, well, all right, well, it's not, it's undefined. Okay. Now here's a couple of interesting cases down here. You can have C be a critical point. Well, actually, these are not critical points. The slope is zero, and yet it's not a critical point. So let me erase this part. Okay, so in other words, it's only the top three that are critical points because one of two things has to be true at a critical point. Either the slope of the tangent line is zero, or meaning that this is a global maximum or minimum, or undefined. Now here, interestingly enough, in this graph, we do have a slope of zero, and yet this is not a critical point because it is clearly not a maximum or a minimum. Okay, and here, because this is a vertical line, the derivative is undefined, and yet still, this is not an extremum because you can see that the slope is not zero. Okay, so these are the cases that we might encounter, but for the most part, what we'll find is that as long as it's a well-behaved function, the critical points will correspond to maxima or minima. Okay, you do get these other oddball cases, but most of the time when we find our critical points, they'll correspond to maxima and minima. And in fact, that's how we're going to test for the existence of maxima and minima. We're going to find all the critical points, if there are any, in a function, and then we'll test them all to see if they're maxima, minima, or neither. Okay. So how do we do this? So we're going to start by setting the first derivative equal to zero, and we can identify all the points where this is true. And then we're going to use another test to determine which of these it might be. Okay, this by itself is not enough to tell us whether this point is a maximum, minimum, or neither. That requires more information. How about this one? 1/3 x cubed minus 5/2 x squared plus 4x, which looks like this. All right, well, it's hard to tell by looking at this function. It is a cubic function, and you know that cubic functions often have this very unique shape to them. It rises, it falls, and then it rises again. And so this is what we have. Now, where do we find critical points? Well, you can see visually, just by looking at it, there are 2 points where the tangent line is flat. So this C equals 1 here, because you can visually see that this is clearly local maximum, this must be a critical. And then again at 4, when C equals 4, the tangent line is flat. The first derivative of this function at 4 equals 0. And the same thing can be said over here. F prime of 1 is equal to 0. And then you can visually see by looking at the graph that this is a local minimum. But there's more formal ways we can do this. So, well, first of all, how did we find these points without looking at the graph? We took the first derivative, and if we notice that it's a quadratic function, which means that we can either use the quadratic formula or else we can factor it to find the points where this derivative is equal to 0. Okay, so remember, when we first started learning about the quadratic formula, the whole point of it was to find the points where whatever function it was is crossing the horizontal axis. And these 2 points, x1 and x2, are known as the solutions of f of x, but that simply means that that's where the function equals 0. Now here, we're not actually solving for where the function equals 0, but instead where the derivative equals 0. But it's the same idea. We're just trying to find where does the function, whatever it is we're looking at, Here it happens to be a derivative. Where is it equal to 0? So if you factor it out, you'll end up with x minus 4 times x minus 1 equals 0. And then you can set those individually equal to 0. And you end up with x equals 4 and x equals 1. So that's how we were able to identify these two critical points. And you can tell just by looking at this derivative that there's going to be two of them. If the derivative had been a cubic function, then we would have had 3. If it was a linear function, we would have had 1. Okay, so we can tell. Now, as far as the identity of these points, we can solve for f of x, the original function, at these 2 points. But it's really, it's the x that's really the important number. But visually looking at it, you can see that the first derivative equals 0 at those 2 points. But now we have to determine if each one is a maximum, a minimum, or possibly neither. Okay, the graph helps, of course it does, but we want to have a formal way of finding whether or not each of our critical points corresponds to a maximum, minimum, or neither. And so there's at least 3 different ways of doing this. The one that I think you'll find is the most commonly used is the so-called second derivative test. So here's the thing we have to think. What is going on with the second derivative? All right, well, let me draw a little sketch here. Keep in mind, the second derivative tells us how quickly or in what direction the first derivative is changing. In other words, the second derivative is the rate of change of the first derivative with respect to changes in x. So for something like this, actually, I'll tell you what, I'm going to draw 4 different graphs here, just so we can see them all together in one place. All right, let's just say this is our function. Well, you can see the first derivative is clearly negative. What about the second derivative? Well, the way to think about it is this. From starting here, when x is a very small number, the slope is extremely negative. That's a very steep slope. And as we move to the right, as x increases, the slope is becoming less negative. So even though the slope is always negative here, as we move to the right, as x increases, it's becoming less negative, which is the same thing as saying that it's increasing. So for this graph, the second derivative is positive. All right, now how about this one? So once again, the first derivative is negative throughout, but this time the slope is becoming more negative. So that means that both are negative. Okay, it's getting a little tight in there. Let me neaten it up a little bit. Let's try that one more time. All right, so in other words, they're both negative. Now let's try this one. Now, clearly, this one always has a positive slope. And not only that, but as we move to the right, slope is becoming more positive. Means both derivatives are positive. And then finally, there's one more case we want to consider. something like that, you can see again, it's positive, but the slope is declining as x increases or moves to the right. So therefore, while the first derivative is positive, the second derivative is negative. So now, when we have a complicated function like a cubic function, there will be regions within which the derivatives, the first and second derivatives can be positive, and regions within which they can be negative. Okay, so let me try that again. Okay, so here the first derivative is negative. I'm sorry, zero. What am I saying? It's zero. So we know that these are critical points. Here's the question. How could you tell algebraically, without looking at a graph, if these are minima or maxima? Well, if you look at the curve carefully, you'll see that in this immediate region here, I'll tell you what, let's call this x1 and x2. The curve is turning down, which means that within this interval that we're considering, the second derivative is negative. Just like on the graph on the previous slide, within the interval here, it's going from down and then up. In other words, the slope is going from negative to zero to positive, which means the second derivative is increasing, and it is therefore positive. So in other words, this is going to help us identify which is which. So according to what we're seeing here, it must be the case that if our first derivative is zero and the second derivative is negative, then we have a maximum. If both are positive, I'm sorry, if the first derivative is zero and the second is positive, then we have a minimum. And you can see just by looking at the graph why this has to be the case. Okay, so this is taken from Symbolab. You can see that it's the same thing. And we went from positive to zero to negative. Oh, it looks like I didn't even label the second derivatives here. All right, so I think you'll find this is very helpful. This is what we're aiming for. If you're using the so-called second derivative test, we need to find first the critical points, and then we need to find out what's happening with the second derivative to determine if it's a maximum or a minimum. What about global extrema? Okay, well, now we've already seen some examples of this. So in a case like this, the global extremum is also the local extremum. In other words, a point can be both local and global. Okay, but there only can be one global. Okay, there could be as many locals as you want, but there can only be one global. So, but of course, the global maximum is also a relative maximum. Or you could think of it in a way as the global maximum is the largest of all the local maxima, and vice versa. Okay. So I guess if we'll encounter other examples of this, but if there's more than one local, and then the global is the largest of the locals. Now, there doesn't have to be any extrema. This one on the left, we've already seen this one, y equals x cubed. Okay. Now, what's interesting is that the curve briefly turns and then rises again right at x equals 0. At this point, f prime of 0 is equal to 0. But There's no maximum or minimum point here. So while it's a critical point, it's not a maximum or minimum. And then here, we have an absolute maximum, but no absolute minimum. And then here, well, we've got a bunch of local maxima and minima, which are all the same, by the way. If you recall the way a cosine works, it's bounded between negative and positive one. So each one of these is a local maximum. Each one of these is a local minimum. We're never going to see a global. It's a cycle. It goes on forever in both directions. Now, let's see, what do we have here? Well, this function on the left is discontinuous. So remember, you've got a discontinuity there, which means the derivative doesn't exist at 2. So while there's an absolute maximum, there's no absolute minimum. Okay. How about this one in the middle? We have a local minimum right here at the bottom of this curve. Now, by the way, these functions are a little different than what we've been seeing. This function actually stops at x equals 4. Okay, you see the way it's been defined down here. The domain of this function, it's x minus 2 squared, but only on the interval 1 to 4. And so you can actually have a function like this that doesn't go on forever in both directions. One of the endpoints can actually be a global maximum or minimum. And that's what happened here. So these are different than the examples we've been looking at. The one on the left is discontinuous. The one in the middle is only defined from 1 to 4. And the one on the left has an asymptote. Well, actually, it's not an asymptote. The range does not include the 2. Well, I'm sorry, I was right the first time. It's an asymptote because it's x over 2 minus x. So that's why the domain can't include the 2. So that means there is no maximum. So these are oddball cases, of course, but we have to be aware that they do exist. All right, here we go. Extreme value theorem. So imagine we've got a function that's continuous over some interval. And this is the closed interval, by the way. It says there must be somewhere in there where this function reaches a global maximum and a global minimum, even if that has to be the endpoints. Like here, the way I've drawn this would be, actually, let me draw that a little clearer. Just to make it more clear, this would be our global minimum. This is our global maximum because it's only defined over this interval. All right, notice we're only guaranteed that it's continuous over this interval. So therefore, that is defined as our global maximum and minimum. So in other words, what we're saying is that the endpoints can be the global maxima and minima. Now, that being the case, remember, it did say that the global minimum maximum must exist. If it's not at the endpoints, it has to be in the interior. There must be one somewhere in there. Okay. So according to this, the global extrema are guaranteed to exist if f of x is continuous. If it does not occur at the endpoint, it must be at the interior. And then it is also a local. So something like this. In this case, the global minimum is here. but this would be our global maximum at the endpoint V. Let's see if I can draw another one. Okay, so obviously this is defined as the global minimum, and this is the global max for this function over this interval. Okay. So in other words, neither endpoint in this case is a global maximum or minimum. All right. So how do we find them? Well, we need to know f of a. In other words, we need to know the value of the function at the two endpoints. Then we can look for any critical points in the interior, if there are any, and then compare them to each other. The largest value of f of x at these points is the global maximum. The smallest is the global minimum. All right, so let's look at an example. Here's a function. It's a parabola. It'll look, let me move this down. Something like this. And the interval we're looking at is one. Actually, let's stick with their. Uh, let's clean this up and start it again. It's gotten very cramped here, as you can see. All right, so we're looking at the interval from 1 to 3. Like this is the 1. And the 3 somewhere in here. So that's our interval right there. All right, so now the points, if you plug these back in, you'll see that f of 1 is -1 squared plus 3 times 1 minus 2. Good. And then for 3, oops, sorry, what did I do there? I just made it the wrong substitution. This is supposed to be a 3. That's better. All right, -9 squared plus 9 minus 2 is -2. So on the graph, we have the points 1, 0, and 3, -2. Fine. Okay, those are the endpoints. Now, the first derivative of this function based on the power rule is minus 2x plus 3. Okay, so what we're going to do is set this equal to 0 and find the points where the tangent is a horizontal line. So here's the derivative. We set it equal to 0. And because this is a linear function, there's only going to be one. Okay, so we have negative 2x plus 3 equals 0. And then algebraically, we rearrange this and we discover that this point occurs when x equals 3/2. So that would be here. And if we need that information, we can figure out what the corresponding value of y is. By plugging this back into f of x. All right, let's just check that out. All right, so that would be minus 3/2 squared plus 3 times 3/2 is 2. And then we'll have minus 9/4 plus 9/2 minus 2. That can be rewritten as negative 9/4 plus 18/4 minus 8/4. So it's going to give us 1/4. All right, so we know that this is an extremum. But, oh, and then right, don't forget, we have to compare, according to this theorem, we have to then evaluate the two endpoints. And so we've already done that actually. Just in case one of those is an extremum. Okay, so we have 1, 0, 3, negative 2. And so the bottom line here is that we organize them all in one place. So the right endpoint is the global minimum. Okay, why is that? Because the function does not take on a smaller value in that interval. Now, we don't have to check all the points in the interior. We only have to check the critical points and the two endpoints. There's the one, we have the critical point at 3/2, and we have the two endpoints. So among all of these, the smallest value of that y that we get is right here. So it implies this must be a global minimum. And then among all these points, the largest value of y is here, which implies a global maximum. So we only had to check 3 points. The one critical value and the two endpoints. We know that the others can't be global maxima or minima. Okay, so that is our extreme value theorem. Now, we're going to move on to 3b. And let's see, I have that open here. Here we go. Now we're going to have another theorem, the mean value theorem. But when this is done, by the way, the theory is, we're going to work our way through the theory, then we're going to get to some more applications, which I personally find them more interesting, but we do need to understand the theory going on behind the scenes. And specifically, we're going to use some applications from economics because it lends itself very well to this, to calculus. In particular, microeconomics is heavily based on calculus. And I'm sure you've all had, micro, macro. No, if not, it'll make sense very quickly. All right. Anyway, so the mean value theorem is the topic here, but we're going to start with something called Raleigh's theorem, which basically says if the f of x are equal at the two endpoints, there must be a critical point in the center. Well, now, by the way, a lot in this at this point, we're not going to see any actual proofs or not very many of them because that, takes a lot more background. But when you get further along, if you do continue to pursue math up to past even calculus 3, what starts happening is that the focus is starting to shift to more proofs than of applications. So like the next course above after calculus 3, sometimes it's called advanced calculus, sometimes it's called real analysis. And that's where a lot of these proofs start to show up, where you start to learn how to actually prove these theorems. And it's a very complex area of study, proofs. But right now, we have to just take the book's word for it that these theorems are true, and we have to wait to find out why by looking at the proofs. So anyway, they're telling us here, like this graph that I drew here, because f of a and f of b are equal to each other, it guarantees that somewhere inside here, the tangent line will be 0. Okay. Now, the one on the left, this is true. The one on the right, no, because f of a is different than f of b. Okay, so here we have some cases where this is true. So for this first one on the left, we've got f of a equals f of b. Same thing here. But not here. Although even in spite of that, there are two extrema in here. Okay, but Raleigh is simply telling us that if the two endpoints have the same value for f of x, then there's guaranteeing us at least one extremum in that interval. So let's say we have this one. Now, x squared plus 2x, I think, yes, this is it. And we're going to only be looking at the interval from -2 to 0. Okay, so what this implies is that somewhere in there, because, oh, and by the way, the function again, it's x squared. Chose these 2 points because f of -2 and f of 0 are equal to each other. Okay, and so we know that there's an extremum in there somewhere. The question is, where is it? Okay, so what you're going to do, as we did earlier, is find the first derivative and set it equal to 0. So based on the power rule, that's 2x plus 2. We set it equal to 0. And that would be this point right here. Okay, x is -1. And you can find the y coordinate by plugging in -1 into the original function. And you can see that at that point, the derivative is 0, which implies a horizontal tangent line. And that is our relative. Actually, in this interval, this is our global minimum. Or actually, for the whole function, in this case, it's the global minimum. Now, the mean value theorem is basically the more general version of Raleigh's theorem, which means here, these two do not have to be equal to each other. So basically, what it's saying here is that as long as the function is continuous and differentiable, meaning there's no gaps, there's no sharp points or anything like that, well, that indicates that there must be some point in there. And let's look at this graph so you can see. If you take your two endpoints and draw a secant line between A and B, we're guaranteed that somewhere in that interval, there's a point whose tangent line is parallel to this secant. Somewhere along the way, we're going to find a tangent line that's exactly parallel to that secant line. Which is the same thing as saying that f prime of c, whatever point we found, is equal to f of b minus f of a over b minus a. Okay. And you can see, well, you're looking at the graph, you can see that f of b minus f of a, think of it as the rise, and the run is this piece, b minus a. That's the slope of the secant. That's why this is why it's written this way. So the secant line that connects the two endpoints, it has a slope of f of b minus f of a over b minus a. And so therefore, we're guaranteed that there's another point where the tangent line has this exact same slope. Okay, so let's try one of these with f of x equals the square root of x. So over the interval 0 to 9, which you can see up here, we're guaranteed there's a point in here somewhere whose tangent line, or the tangent line at that point, is the same as this secant line right here. Now, here's the formula for finding the secant line. F of 9 minus f of 0 over 9 minus 0. But f of 9 is 3 because it's the square root of x. F of 0 is just 0. So you can see down here, it's 3 minus 0, 3 minus 0 over 9 minus 0, which is a third. So that means the secant line here between the two endpoints has a slope of 1/3. And so we can find another point in here where the tangent has a slope of 1/3. I don't remember why I wrote that in here, but increasing, this is an interesting word in math, monotonically, just so we can discuss this for a second. Monotonically increasing simply means that if, let's say we're looking at 2 points, x1 and x2. If x2 is greater than x1, then f of x2 is greater than f of x1. And so in English, that just means that the function continues to rise. There are no portions of it where it dips down again. Like down here, for example, this one is not monotonically increasing because there's a portion where it dips down before it starts rising again. This one is monotonically decreasing. So you can see the reverse is happening. If x2 exceeds x1 and f of x1 is greater than f of x2, and that's for all x's in that interval, by the way, not just those 2 points, but for all of them, then the function is increasing or decreasing monotonically. Okay, now this has useful implications. For example, if a function is monotonic like this, then that guarantees that it has an inverse, for example. And it can come in handy in other applications. But here, we have our interval. We've already proven that the slope of this tangent is a third. Okay, here's 0, here's 3. So what we need is to find that point in the interval whose tangent line has a slope of 1/3. So here's what we're going to do. Since the function is x radical x squared, x rather, which is the same thing as x to the 1/2 power, from the power rule, that means that a is 1 and n is a half. So the derivative therefore be a half times 1 times x to the 1/2 minus 1, or 1/2 x to the minus a half, which could also be written as 2 over radical x. So we're going to set that equal to a third and solve for 1/3. And so we see that this gives us 9/4. Okay, so 9/4 would be somewhere around here. And at that point, what this is telling us is that the tangent line has a slope of 1/3, just like the secant line between the two endpoints. Okay, here's a much nicer version of that graph, but you get the idea. So one important corollary, which means one of the implications of it is that if f of x is continuous over this interval, n differentiable, and by the way, if you notice the way this is written, they're leaving open room for the possibility that it's not differentiable exactly at the endpoints. But inside this interval, the function is both continuous and differentiable. F prime of x is positive. The slope is positive. That means that f of x is what they're calling increasing or monotonically increasing over AB. If f prime of x is negative for all the x's in that interval, then we have a monotonically decreasing function. So this is one way we can identify if a function is monotonically increasing or decreasing. Okay, so now here they're showing you that it can be increasing or decreasing only within given intervals. It doesn't have to be the case that the entire function is increasing. But what they're saying is that within those intervals, if these conditions are met, then what we're going to have here is increasing or decreasing. This looks a lot like the graph I was just showing you a little while ago, doesn't it? Okay, well, not a problem. We've already discussed this, except that here, what they did not do here is I did not show you the second derivative. So the function is monotonically increasing, and the second derivative is positive. Here it's negative. Down in the bottom left-hand corner, monotonically decreasing. The slope is getting more negative. And here it's becoming less negative. One of the implications of all this is that if the function goes from increasing to decreasing within an interval, that guarantees the existence of a maximum point. If the function is decreasing and then increasing, that guarantees the existence of a minimum point. But of course, keep in mind, this assumes that the function has to be continuous in the entire interval. And of course, the derivative has to exist. Oh my God. Now look at this function. Can you imagine what the actual equation looks like? So you got all these regions with all these different things taking place. You got four critical points, and three of them, the tangent is flat. In this first case over here, the derivative is undefined. And you can tell by the signs whether it's a maximum or minimum or neither. This one is not an extremum. This one, of course, is a max. This is a local minimum. And this one is also not an extremum. Okay. So in other words, this is one way we can define whether or not any of these points, critical points, I mean, are relative extrema or not. We call this the first derivative test. What we're looking at is the sign of the first derivative and how it changes. I wrote this, sorry, this is a relative max. It says it right there. I wrote the wrong thing there. This is a relative max, local min, neither, and then local max. The way you can tell is by looking at the sign changes. Now, the diagram left out this part here, I see. But see, here's what I really want you to notice, because it's the only case where we do not have an extremum. Oh, now you see, this is sort of a hint. Why is it the case that this is not an extremum? Because the first derivative is positive on either side of it. That's the key to the whole thing. It doesn't change. Okay. So in this first case, it went from negative to positive, making it a maximum, negative to positive, minimum, um, zero, positive to positive means not an extremum. And then, of course, positive to, um, oh, there's a goof up here. No, this is a typo. God, that scared me. There's a typo in this diagram. Okay, yes, that's fine. So wherever the first derivative changes signs, that is an extremum. So we identify the potential extrema with these critical points, and then we check them with the first derivative sign. This is what we mean by the first derivative test. With the second derivative test, we're just looking at the sign of the second derivative. We don't need to compare it. It's just either it's positive or negative. But here we need to know what it is on either side of that critical point. Okay, so we're going to look at the, oh my God, look at this one. It's a cubic function, x cubed minus 3x squared minus 9x minus 1. Now, if you were to take the first derivative and set it equal to 0, you would be able to identify all the critical points. So we'll do exactly that here based on the power rule, 3x squared minus 6x minus 9, which, by the way, in a case like this, you can simplify it by dividing out, they all have a common factor of 3. And you'll find that if you do it that way, you'll still get, I mean, you'll get the right answer either way, but this way, if you want to factor it, it'll be simpler to factor it, or else you can just plug this into the quadratic formula. But you'll see that if you factor this, it's going to be x minus 3 times x plus 1. And so we set those equal to 0. Those are going to be our two critical points. And so the interval is actually broken up. Then there's actually three intervals to consider. All right, let's look at this. Everything leading up to -1, everything from -1 to 3, and everything from 3 up to infinity. And I broke it out. I wrote these Roman numerals here. Think of these as different regions, I guess. Region 1, everything up to our first critical value. Region 2, everything down to the second one. And then region 3 is everything up to the third one. And all we really care about here is the signs of these derivatives. Now, you can tell just by looking at the graph, but you could also do it. What you could do, for example, is you could actually calculate the first derivative on either side of this function. I'm sorry, the critical values. Like you could evaluate this as f prime of, let's say, -2 and positive or 0, let's say, and look at the signs on either side. But by looking at the graph, you can see clearly that the first derivative is positive throughout region 1, negative throughout region 2, and again positive in region 3. And because of the sign changes, see that this point must be a relative maximum, and this point must be a relative minimum because of the change of the signs of the first derivative. Okay, so now we have some more interesting results. This notion of concavity and points of inflection. So this is where the second derivative starts to get involved. If f of x is differentiable over an open interval, and the first derivative is increasing throughout that interval, f of x is said to be concave up. Otherwise, it is concave down if f prime of x is decreasing. So now again, this is a graph that we saw earlier. We didn't use this terminology. For example, in this case, we know that the second derivative is positive, as is the case directly below it. And that's all it takes for us to conclude that the function is concave up. Over here on the right-hand side, the second derivative is negative in both cases, because up here in the upper right-hand corner, the slope is going from staying positive, but it's decreasing. And the bottom right-hand corner, it's becoming more negative as we move to the right. So the second derivative is negative, and that is what we mean by concave down. Okay, now, also you can tell just by defining a secant line through the two endpoints. Concave up, by the way, concave up sometimes is called convex. If you define a secant line between the two endpoints and it is everywhere above the function, that means it is convex, a concave up or convex. Okay, so in other words, those are the ones that are concave up. Here it's the other way around. Okay, And so again, you can tell this is more geometry. You can tell by looking at the relationship between the function over that interval and the secant line. So now, though, we're going to use a more formal test. And we're going to claim that as long as f of x is twice differentiable, meaning that f double prime of x exists over a given interval I, then a positive second derivative, as we've already seen, is concave up. Second derivative is negative. That's what we mean by concave down. Inflection points. Now, here's the one of the strange things that can happen. If f of x is continuous at a, and the concavity changes at that point from up to down or down to up, then we call that an inflection point. So let's see if we can, it's hard to visualize what this looks like. So here we have an inflection point because if you notice, the curve is in this first interval up to a concave up. But then all of a sudden it's concave down. How do you know? Because if you notice the slope is flattening out. It's like imagine that you let's say you are skateboarding down a hill, a very steep hill, and you're going really fast. And then as you start to go back uphill again, you start to slow down. You're still going forward, but you're slowing down. So at this point where you're starting to decelerate, suddenly the second derivative is negative, and we call that an inflection point. So that's the point where there's a change from a second derivative that's positive to negative, or it could be the other way around. It could be from negative to positive. All right, so let's look at this one for a second. X cubed minus 6x squared plus 9x plus 30. We're going to find all the intervals where f of x is concave up, concave down, and find any inflection points if there are any. All right, well, here's the function. I think you can tell just by looking at it, this is what we're aiming for. This is our inflection point. So what we're going to do is take the first two derivatives. And again, we're just repeatedly applying the power rule because this is a polynomial. And so here's the first and second derivatives. So first, we're going to find the points where, if any, where the second derivative equals 0. Why is that? Because if you look at this graph very carefully, you'll see that the second derivative at exactly this point is exactly 0. That's when it switches from positive to negative. So by setting it equal to 0, we can identify any inflection points there may be here. You can see it's equal to 2. And you can find out the y coordinate by plugging 2 into the original function. It turned out to be 32. So you can see also, if you look at the second derivative, for a point left of 2, for example, f double prime of 0 is negative, which is, you can see by looking at this graph. This is like the slowing down portion. It's increasing, but at a decreasing rate. So the second derivative is negative. On the right-hand side, it's the other way around. The graph, it's basically accelerating. And so if you test that interval on the right, you'll see that, for example, f double prime of 3 is 6, which is positive. And we've already seen that at exactly at this point, f double prime of x is 0. Okay. So therefore, we have ourselves an inflection point. Now we can also, if we want, go ahead and identify the maxima if we want. But to just find the inflection points, this is all we have to do. Oh, and also, yes, if we want to use our new terminology, over here we have concave up, and over here we have concave down. Okay. Wow. So then we can go ahead and apply the first derivative test to identify the minima and the maxima. So here's the second derivative test. This is the formal definition. If we find a function where the first derivative at that point C is equal to 0, this is our critical point. And the second derivative has to be continuous and exist, of course, in the first place. When the second derivative is positive, then that means that we have a minimum at that point, C. Negative means it's at local maximum, and 0 means the second derivative test fails. Oh, see, now that's a strange result. The test can actually fail, which means we have to try something different. All right, let's look at this one. F of x is x to the fifth minus 5x cubed. Use the second derivative test to find all the local extrema. Oh my God, look at this thing. So we have three candidate points for three critical points, I should say. Remember how that works? We take the first two derivatives. So we can find our critical values, remember, by setting the first derivative equal to 0. And it turns out that the first derivative is actually it's a cubic equation, which means we have potentially three critical values. And although I've broken it up a little differently here, just to find the solutions more quickly, we're going to set 5x squared equal to 0 and x squared minus 3 equals 0. So the critical points are 0, positive radical 3, and negative radical 3. So those are all potentially at least maxima or minima. We know that they're critical points. And what we're going to do is figure out which is which by taking the second derivative test. The second derivative turns out to be 20x cubed minus 30x. So we'll start with 0. Now, here's the interesting part. You can see by looking at the graph that this is not an extremum. So the second derivative is actually 0 at that point. What about the other two? Negative radical 3, the second derivative is negative. Fine. At radical 3, it's positive. Okay, so we have a negative second derivative here, positive second derivative here, which implies a relative maximum and relative minimum. Here, what we need to do is try a different test. It says here inconclusive. That usually means there's other things we can try. And we also can remember we can identify these as concave down and up. Okay. We'll get back to that, by the way. What do we do about this inconclusive test? You actually can go on and conduct a higher order derivative test. Like there's a third derivative test and a fourth. And what'll happen is you'll keep going until you find what you need, because eventually you'll have to find the value that you want. But it's not guaranteed to happen with the second derivative. All right. So that's pretty much that is our discussion about maximum and minima for now, at least. Um, we'll certainly see a lot more of this as we go along. But these are the underpinnings of what we'll be doing when we study optimization techniques. And so what this is followed up by 3C, which is L'Hopital's rule. Now, L'Hopital's rule is a way of finding limits when direct substitution leads to a very bizarre result, like 0 divided by 0 or something like that, or infinity over infinity. So in other words, there are rules. If you recall, when we started doing limits, there are rules that will enable us to handle cases where the results are very strange. And so L'Hopital's rule is one of them. It's a very helpful rule. And what else is there in this chapter? Let's take a look. There's also a 3D, remember. I want to remind myself what's in there. Antiderivatives. This is sort of a bridge into the next chapter. What we're basically doing is reversing the differentiation process. And I don't want to break the bad news to you, but this is actually more complicated than taking derivatives. But it's awfully, awfully important. So anyway, I think we'll knock it off right here. So we're done with 3A and B now. And so we're kind of selling along here. And chapter 4 is all about what we call integration, which is the reverse of differentiation. And then after that, well, we'll be doing a lot more interesting things. So, all right, I'll see you all next time.